So you guys are able to see my screen?
Yes, sir.
So good evening, everyone. Today I'll be conducting the problem solving and doubt clearing session for the course Digital Control and Switch Mode Power Converters and FPGA based prototyping. So this course was conducted by Professor Dr. Santanu Kapoor from IIT Kharagpur, and I'm Calvin Joseph, and I'll be conducting this doubt clearing session. So this doubt clearing session happens every Tuesday from 6 to 8 p.m. You can ask your doubts. So the outline of today's presentation is today I'll be discussing about how we'll be running simulations in MATLAB and Simulink, where we'll be discussing about how the files are made, how the models are made, how the codes are run, etc. So that we can run the simulations of the various control techniques, the various modulation architectures, and run it and simulate it and try to get an understanding about their operation and verify what we have learned in theory that is happening. This is also just a simulation level, and it is easy because you guys will have access to MATLAB and Simulink. So as you are taking part in this course, you will have access to MATLAB and Simulink, and you can use the software for running all these simulations. Next, I will be discussing about analog control and modulation techniques. So we have already covered what are the various analog control techniques are there, such as analog control, etc. The various modulation techniques such as fixed frequency, peak current control, value current control. Yes, yes.
Sir, your voice seems to be not clear. With some noise, it is.
Noise. Now is it clear?
Not little bit less clarity, sir. It is not breaking, but
okay.
It is coming with noise.
Okay. Noise is there. So is it like some external noise or anything? Can you describe it?
No, not external noise, sir. It is.
Okay.
Yeah. Now, when you speak louder, it is good. Yeah, your voice is not.
Okay. Okay. So now it is clear.
Yeah. Now it is clear, sir. Yeah.
Okay.
Yeah, it is clear.
Okay, so first I'll be discussing about how we will run simulations in MATLAB and Simulink, how we can use these softwares and how the various files and codes, etc. we can write and we can create, and so we can run the simulations. Then I'll be discussing about how we can how about the various analog control and modulation techniques, which we have already learned in the previous weeks, and we can have a recap of them and we can see how the Simulink files or MATLAB codes, etc. are available. Then I'll be discussing about the digital building blocks. So now we have studied analog control. We have understood how analog control works, and now we want to digitize it. So we have briefly discussed about how we digitize it, but how we will make those digital blocks in our Simulink, that is an analog to digital converter, as well as our actual PID controller, etc. How we will make it in Simulink, I will be describing that. Then I will discuss about how we will implement digital voltage mode control in MATLAB. What are the various blocks which are required? What are the various files? How do we run it, etc. And what we will observe, that we will discuss. Next, I will also discuss about mixed signal current mode control. This is current mode control in which the voltage loop is digital, but the current loop is in analog domain. So hence it is known as mixed signal current mode control. Also, I will discuss about digital current mode control, where both the voltage loop is in digital domain as well as the current loop also is in digital domain. So it is known as fully digital current mode control. Next, we will also run some various files, simulation files for variable frequency current mode control. As we have seen in this previous weeks, there are basically three main types of variable frequency current mode control techniques, which are constant on-time control, constant off-time control, and hysteresis control. So we will discuss about these techniques and we will proceed with the lecture. So next we will talk about. Okay. So now we will proceed to how to run simulations in MATLAB and Simulink. So the advantage of MATLAB and Simulink is in this course, there we have discussed about various control techniques and how we will write FPGA code, etc., and we can test and verify it. Also, there was a hardware demonstration also are available in the later weeks of this course, but that might not be possible for everyone to do. Like you might not be able to physically, you might not be able to design a PCB, you might not be able to have an FPGA because of various constraints and other stuff. So it might not be possible for you. But then using MATLAB and Simulink, at least you can get a brief understanding of these control techniques of how we do sampling, how what is the logic in the control technique, how the performance of how we can compare the performance of one control technique to another control technique or one modulation technique to another modulation technique. So all simulate in MATLAB and Simulink. And this is it will give you a lot of insight into the operation and it will build your understanding about the concepts which you have covered. Uh, Also, MATLAB and Simulink is available for you guys because you have if you have enrolled for the course, the license, limited license, the license is available for a limited time for you guys and you can use it. Right. So what are the various control techniques you have learned you can implement on MATLAB and Simulink. So now I will discuss how we will do it. So if you have gone through the videos, like so the professor is using is simulating the code and he's also running a Simulink file. So first I will consider this is known as a .m file. There is a .m file which is there in which I will write my parameters or gains or other factors. I will write it in my .m file. So in this .m file, I'll be calling a buck parameter, buck underscore parameter. So this buck underscore parameter is another file, which is the which my wait, I put pointer. So buck underscore parameter is this file. This file is my buck underscore parameter. So all the parameters for the buck converter which I am using, the power stage parameters, etc., I will write in this file. This is the value of my inductance, the value of my capacitance, the switching time period, the DCR of the inductor. So we know that an inductor will also have a resistance. So that's the value of the resistance. The on resistance of the MOSFET, on resistance of the low side MOSFET, the capacitor ESR. So the capacitor will have its capacitance plus an equivalent series resistor. That is known as the ESR. Okay, then the input voltage to the buck converter, the reference output voltage, all that I list down in this buck underscore parameter .m file. Now, when I call this file over here by buck
Sir,
underscore yes, yes.
sir, this RD is the resistance of the diode.
Yes, yes, yes. Listen to the diode.
And VD is 0 into 0.55.
Yeah, we've just included that and we can write as 1 into 0.55.
Okay, this is forward drop. Okay.
Yeah, the forward drop of the diode. So in these simulation files, in that Simulink model, the custom Simulink model which was made, there's a provision that we can run the buck converter as either a synchronous buck converter or as a asynchronous buck converter. So the difference between a synchronous buck converter and asynchronous buck converter is in a asynchronous buck converter is like a conventional buck converter. There's that diode is there for the freewheeling operation. But in a synchronous operation, instead of the diode, we replace it by a MOSFET. The advantage of we using a MOSFET is that the drop or the resistance drop of the MOSFET is less. So the losses is less if we use a MOSFET in place of a diode. So for when we want to improve the efficiency and other conditions, we use this MOSFET instead of the diode. That is so one is a synchronous operation, synchronous buck converter, other is a asynchronous buck converter. Also, there's a concept of let me draw pen.
Sir, actually, you are saving this file in this name and again calling this here.
Yeah. We're saving this file. Okay, that the buck converter thing I will talk about later. So first I will talk finish this and then we'll proceed. So so this file is called by this line buck underscore parameter. So it is important that all these files be located in the same directory or in the same folder. Okay. So I call this buck underscore parameter file. Then f underscore sw is my switching frequency. Okay. So that is 1 upon t. That is 1 upon the time period t, which is defined over here. Input is 12, the reference is 1. We are writing it twice, so it gets overwritten. So the latest value, it will consider it. Okay. R is 1 means the resistance is 1. Now modulator gain is VM10. We will discuss about this. And the PID controller also, the values are set. How we design the PID controller, etc. Those will be discussed later. How we will design it will be discussed in later weeks. But now certain values of the PID controller are provided, and we're using those values to simulate our simulation. All right. So KP is there, KI is there, KD is there. Here KD has been set to 0. Now we will use that to get the transfer function. So the transfer function has a numerator and the transfer function has a denominator. So these are the coefficients of the numerator polynomial and these are the coefficients of the denominator polynomial. And using this line of code, GC is TF transfer function, which is the numerator coefficients and the denominator coefficients. We can generate a transfer function block. Now we can generate the transfer function system. All right. And that we will be using in our Simulink file. So this is the line of code which will generate GC. It is like a transfer function, which I will use it in my Simulink block. So the advantage of this method is I can change these values. Okay, I can change the inductance value in this line of code and I can run it. So, but the problem is if it was not like this, then every time in my Simulink file, in the value of inductor, I'll have to change the value of L. And if that L is used in repeat many different places, each time I have to go and update the value of L. That would be time consuming and it could result in errors. And then we will not know where is the error, where did we make the mistake, etc. So in this way, when we write it in a structured format and we can update the values based on our requirements, and that updated value will be reflected in all other places where this variable will be used, is one advantage of using this method. Okay. So this is the set of simulation. This is the first set. Next, I will go on. You can have a further list. Okay, that file is not yet complete. There's further options. So I can select what type of control method I want to use. Whether I want to do voltage mode control, current mode control, constant on time, this is constant off time current mode control. So peak constant COT means constant off time current mode control, and valley COT means for constant on time control. So all this, like these .slx files, these are Simulink files. Okay, Simulink is a graphical user interface where we can use blocks, etc., to make a model which we will simulate. So there were multiple models created, and these are the various options. So it is important that these models or these .slx files be stored in the same directory or in the same folder where your .m, this file of MATLAB, is present. Okay. Then this enter file name is equal to op3 means I've chosen this file. I've chosen this peak constant on time current control as my file. Okay. Then transient parameters and plots is like some tsim stands for the simulation time period. T step stands for the instant at which I give a step change. Okay, I give a step change. So the step change can be a change in the load current, can be a change in the applied input voltage, or it could be a change in the reference voltage. So these are just some variable values which I've assigned, and I will be using those variable values, these variables, in my Simulink file, and I will be performing my requirements. Okay. Now buck converter simulation is another .m file which I will touch upon later, and plot underscore buck is another .m file. So in this file, this file has a code for running the simulation. This file this file plot underscore bug has the code for plotting the results of the simulation. Okay. So
Sir,
yes,
sir, this buck converter dot underscore voltage mode control dot SLX.
yes.
Okay. Actually, this is the file. The output of the controller will be stored in this file.
Output of the controller. Which controller?
No, this we are saying this controller method OP1 equal to this one.
Okay, no. This OP1 is like just a name. See, this buck underscore converter underscore voltage mode control dot SLX is a Simulink file which is made for
Okay.
performing voltage mode control. Next one is another Simulink file which is made for performing peak current mode control. So they are different files. Now I want to
Yes.
decide which file I want to run. Okay. If I want to decide
Okay.
which file I want to run, I assign each file a variable name. Okay. I've assigned it a
Okay.
variable name OP1. I've assigned this a variable name OP3. Now I decide this enter underscore file name means I've selected OP3. It means I am going to run this peak constant off time convert control. I am selecting this file to run. Okay. So
Okay.
this
The similar means in terms of blocks.
no, yes, Symlink is in terms of blocks. So each
Blocks.
.slx
Okay.
file is a different Symlink file. Okay, .slx
Okay.
file is a different Symlink file, and that Symlink file has different blocks, lots of blocks.
Okay.
Okay,
Okay.
we'll touch upon it. I'll show it further. Okay.
Okay. So in the previous step, in the previous slide, you have modulator gain.
Yes.
This is a PW modulator gain.
Yes. PW modulator again.
Okay. This is modulating frequency.
Which
Okay.
one?
This FM.
FM is not a modulating frequency. It's a modulator gain. Like see, VM is the maximum value of the modulating ramp, and FM is equal to 1 upon VM is the the modulator's gain. Yeah,
Okay,
okay,
sir.
I'll see. Is there any doubt in this, or should I draw a waveform and show?
Okay.
Hello, sir, am I audible?
Yes, Ted. Now,
Sir, what is this FM? You are going to say something on this topic.
okay, 1 minute. So,
Sir, are you speaking? We couldn't
no,
hear you.
just 1 minute, just 1 minute. I was connecting something. So now, can you
Okay.
is it getting written anything? 1 minute. It's got stuck. Just hold on. No, it's got hanged.
First slide is showing. First slide is showing, sir.
First, let me show you.
Yeah.
So now are you able to see my screen?
Yes, sir, able to see.
So now see, this is known as a modulating ramp signal. Okay, this is used in voltage mode control. So this is 0 and this is the value of Vm. Vm is the maximum value of this ramp signal. Okay. Now, when I have some compare signal Vc, okay, this is a compare signal Vc. So my duty ratio will actually be equal to Vc upon Vm. Okay. So when I will see this PWM block, this is my PWM block, I apply an input Vc, I get an output D. So effectively the gain, that is effectively the gain of this, that is D upon Vc, which is equal to 1 upon Vm, is equal to Fm, is the gain of this modulating block. Right? Any doubts in this?
Sir, why this
Sir,
D
what
by
is the
VC?
use of it?
Okay, one question at a time. So use of this is this when we are doing modeling of these converters to find out the gains, PID controller gains, etc. We have to consider this gain of this modulator. So that is the use of it. Okay.
Yes, sir, further to D equal to Vc by Vm is enough. And why you are introducing Fm equal to 1 by Vm then?
No, I am just writing 1 by Vm is equal to Fm. That's all. I'm not introducing anything. It's just a notation that Fm is equal to 1 upon Vm. And Fm is the gain of this modulator system. The gain of this modulator system, I'm denoting it by Fm, and the value of Fm is equal to 1 upon Vm.
Sir, always gain is said in terms of output upon input, right?
Yeah.
But here, like 1 by Vm, how it is making sense in terms of gain?
No, see
Yeah,
here.
D by VC is output gain.
See here, D is my output and Vc is my input. Okay.
Okay.
So this is the gain of that system is D upon Vc, and that is equal to Fm, which value is 1 upon Vm. Any more?
Yes, sir.
Hmm.
Understood, sir.
Okay, fine. So Ajay, Lakshman, you have any queries also you can ask. Can you send a message? Or you could also unmute and you can ask me. Okay, wherever you're having issue, you can stop me and you can ask me. Right?
Okay.
So
Sir, like, sir, 1 upon Vm is always constant, right?
yeah. Hmm. So this is a system with constant
But,
gain.
sir, yes, sir, once,
Hmm.
please back to previous slide, please.
Yeah. So the why today is creating issues. Yes. Okay.
Sir, here, if
Hmm.
like here my Vm is always constant and based upon the Vc,
Hmm.
the duty ratio is changed, right?
Yes.
But
So VC
Fm is
changes.
always constant.
Yeah, FM is like a constant gain. It is like FM is the gain of that modulator block, so that is constant. See, actually what will happen is this VC will change. Once it will be this much, then it will become this much, then it will become this much. So my VC is what is changing my duty ratio. This is my control. VC is what is changing my duty ratio. If VC changes, then my duty ratio changes. Okay.
Yes.
So these are the variable values which I have stored in my .m file. Next, I have this file where I select which Simulink file I'm going to select for running the simulation. Now I will talk about this buck converter simulation file. I'll talk about it. So this is my buck converter simulation file. So it has the initial conditions. DC enable stands for whether I want to use my converter as a synchronous buck converter or as a asynchronous buck converter. If I set it as DCM underscore EN is equal to 0, that means I'm going to use it as a asynchronous buck converter. And that means I'm going to use it as a synchronous buck converter. That is, I'm not permitting discontinuous conduction mode. See, what is discontinuous conduction mode? Suppose this is my inductor current. Okay, it rises. This is my time. This is my inductor current. The inductor current is like this, means it is operating in continuous conduction mode. However, if the inductor current is like this, it goes up, it falls, and it remains at 0 for some time. Then again it rises, again it falls, remains at 0 for some time. This is known as my discontinuous conduction mode. So this discontinuous conduction mode occurs when my load is less. If the load is less, then my inductor current also will be less. And for some duration of the operation, it will remain at 0. Okay, because why this happens is because my diode cannot allow current to flow in the negative direction.
Sir, this DCM
yeah.
mode of is possible with synchronous buck converter too?
Yeah, it is possible, but we'll have to be able to identify when that inductor current has touched 0, and we will check. And then we must turn off the MOSFET, etc. So that it will require some sophisticated control algorithm, etc. But it is possible.
Okay, sir. Okay.
So these are the two conduction modes which are possible. Also, I will set the initial value of the inductor current like to be around 1 ampere. My capacitor should be stored at around 1.1 volt. It is charged up to that value. So see, because the inductor and the capacitor, they are energy storing elements, and they will have history. They will have. You need to know what was the previous value, how much inductor current was previously flowing, how much capacitor voltage was present, etc. So that's why we write down we initialize those variables. Next, I will simulate the file. So I open this command open means it will open the Simulink file, and this command sim means it will simulate the Simulink file. It will run the Simulink file. Okay. So when I execute these commands, it will open the file and it will simulate the file. Next, I want to read the data. Now, after it finishes simulation, the data which is available, I want to use that data and I want to plot those results. So this is the line of code which will take the time data, then I multiply it by 1000, so I'm converting it to milliseconds value. The next is like I am accessing the vector data, and that data the first column is my inductor current. My second column is my ramp voltage. Third column is my output voltage. Fourth column is my VCOM. So all these data I am accessing one by one. Okay.
Sir, sorry to interrupt you. Sir,
Yeah,
why you are mentioning X as like vector?
like it has a number of this X. It's like a table. Okay. One is my inductor current. One is my VRAM. One is my V output. One is my VCOM. Okay.
Yes,
And
if it is said as an array, then it will be okay. But you are saying vector.
plus it is a column, right? It is a column. That's right. Exactly what is the definition of vector, or that probably then my terminology is wrong. But effectively what it is the inductor, the data values of inductor current is in a column, in one single column. So that I want
Sir
to
also said the same. It is a vector in the lecture.
see, um, we consider, because it is a large number of data points, so we consider it to be a vector. But how to explain exactly, I am also not able to remember right now.
Sir, here we consider each column as a vector, is it?
No. See, this is X is the first row of X consists data of inductor current, of ramp, of output voltage V count. That is why it is a vector. The X is a vector. Okay. And X2 is another vector. X3 is
Sir,
another
if it
vector.
is, sir, if it is an array, it will be okay. But you are saying it's a vector.
No. See, let us consider this row. This row. Okay. It has the data of inductor current, it has the data of ramp voltage, it has the data of output voltage, and it has the data of V count. So that's why it is a vector consisting of these values. And then I have the aggregated sum of all those vectors, and that effectively is my X. Okay, it is
Sir,
not
can I ask
important.
another question?
Yes, ask us.
Sir, this DCM enable equal to 0 means we are we are trying to operate in CCM.
Yes. If DCM enable is equal to 0 means I am operating in CCM.
Okay. Sir, now in this column, in this table of the inductor current, V ramp, output voltage, so we are taking T time.
Hmm.
We are this a T scale.
Yes.
So that does each row of this column, each row of this table has a time.
Yes, so time is like
Uh,
this. This will be time at 0, time at 0.1, time at 0.2.
okay.
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 So
Okay.
what I need is my inductor current at time 0, what were those values? Now, then at 0.1, what were
Okay.
the values? All that. Then if I have this data, then only I can plot it. Right. So
Yeah. Okay. Sir.
there are means to get the value of time instance and get the value of the recorded data of these ILB RAM V output VCon, and that we will be using in our plots. Okay.
Okay.
Sir, if
Sir,
I like DCM enable is a 0, like if I am operating in continuous conduction mode and if the load is very light load, then
uh,
it is possible to have discontinuous conduction mode with the
no,
DCM enable, right?
I'll show you. So this is my time, this is my inductor current, and my load current output is low. Okay, so it's operating light load condition. What could happen is the inductor current would operate like this. Okay, so the inductor current will partially go in negative because my MOSFET enables conduction of current in both directions. But if it was a, so that's why this is synchronous operation or CCM operation.
Okay.
Now, depending on the application, we may want it to be operate in this way. We might prefer to operate like this, or we may prefer it to operate like this for light load condition. That depends on our application, how we have designed, etc. But it is possible.
Okay, sir.
sir, in synchronous converter, uh,
Hmm.
during the off time when the inductor is discharging,
Hmm.
at that time the MOSFET will conduct.
Yes.
The
So,
MOSFET connected to the ground will conduct.
yes. That MOSFET connected to the ground will conduct. And like, let me just show. See, this is for the conventional buck. So buck converter we don't have one. So if you see this over here, okay. So I'm audible, right?
Yes, sir.
Okay, it's clear, no? It's not soft, etc. Right?
It is clear, sir.
Okay. So this is my synchronous MOSFET. Okay, this is my complementary MOSFET. So as long as I give this value 1 over here, it will conduct. The current can flow like this in this direction also. The current can also flow in the reverse direction as well. If it is flowing in this direction means the current is positive. If it is flowing in this direction means the current is negative. But as long as the switch is turned on, then it will operate. Then the MOSFET will be on and it can conduct current in either direction depending on the external inductor current which is forcing it.
Sir, is there any specifications for a particular switch you use it to be in high side and low side? What is the difference, sir? High side and low side they are mentioning.
No, this is low side because it is connected to the ground. This switch is low side switch because it is connected input pointer. So
Okay,
this switch is my low side switch because it is connected to the ground. This switch is my high side switch because it is connected to the input high voltage.
okay. If I interchange those two, is there any problem?
No. They won't be a problem because they are designed for that. No? They should be able to withstand those voltages.
Yes, is there any difference on the voltage stress applied on the high side switch is less, more, and this has less? Is there anything like that?
See, just consider when the high side switch S is on. Okay, this is on. That means the voltage. That means the switch S bar is off, and the voltage I applied to this VN. Okay, VN is the voltage applied to it. So my low side MOSFET should be rated and capable enough to withstand VN. Okay, and we select 2 times into VN, etc. for safety. Okay, we have a safety factor, all that. Now, let's consider high side MOSFET. Okay, when the switch S bar is on, that means S is off. So the voltage across this is again VN. Okay, it is again VN because this is connected to ground. This node over here is connected to ground. Then the effective voltage across this MOSFET is VN. So both my MOSFETs are rated, have to be capable of withstanding voltage VN when they are off. And we have some safety factor and we multiply it by some other value, some other higher value, so that it should safely withstand voltage of VN.
Okay.
Sir,
Yeah.
sir, can you please once say the operation of this when the top switch is on,
Uh,
when this S is on, this inductor will charge. That is the usual operation.
yes. Yes.
When we switch off S and S bar is on,
Uh,
then again this diode only will come into the conduction. How does the MOSFET, when will that MOSFET on the low side will be coming into conduction?
okay. Yes, understood. So this is my IL, okay, my current IL. Huh?
Okay.
It is on. S is on. Now I turn off S, and it will reduce. Okay, the current will start decaying. Hmm.
Yes, sir. Yes, sir.
So S bar, if it is on, if S bar is on, okay, S bar is on, then the current will flow through the MOSFET. Okay, through the MOSFET it will flow. See, what will happen is it will have two paths. It can flow through the body diode of the MOSFET or it could flow through the channel of the MOSFET. So if the Q bar is high, if Q bar is 1, that means the current can flow through the channel of the MOSFET. See, it depends, okay? Depending on the effective resistance in parallel, it will try to go to the path of least resistance. So prefer to flow, majority of the current will flow through the channel of the MOSFET. Okay. Now, in
Sir, but
case,
MOSFET,
no, this once it is, if the MOSFET is turned on, okay, if the MOSFET is, the channel is formed, then it can conduct current in both directions.
then this diode becomes,
See, this is actually a very high level thing. Okay. There are
okay,
papers, I think Texas Instruments and all, they have papers for buck converter, synchronous buck converter, and you can try to
okay,
understand it. So what the point I want to stress on is, like over here, okay, if the inductor current is falling, okay, if S bar was not on, it would stop off over here and it would continue to remain at 0. But if S bar is on, it will further continue to reduce. Okay.
okay,
That is the point we noted. And that is what is currently required for this level of the course. In your research and all, you can further try to figure out when do we want to use synchronous or asynchronous buck converter. Okay. So I'll go back to the plotting of the MATLAB codes, etc. Because we have lots to cover. So now if I want
okay,
to
sir.
plot the results, okay, I want to plot the results. So I have this set of code. So subplot means I have one figure 1. Okay, this is my figure 1. Assume this is my figure 1. This is my subplot 1. This is my subplot 2. So this is in subplot 2, first row, first column. So our first column, first row. Subplot 2, first column, second row. So this is my one. I have one column and it has first row and second row. Okay. So I have two subplots. In one figure, I have two plots. Okay. Then plot is time versus inductor current. So this is my time and this is my inductor current. But here what I will plot time, and here I will plot my output voltage. Okay. And these are certain lines of code, to now Y label means stands for the label I give. Label over here. I will give a label here that this is my inductor current. I will write it over here. Here I will give this, then I will give this over here. It's an X label time millisecond. So this means I will write over here time millisecond, etc. And here again, Y label is given means V output. I will write that this is my output voltage in volt. So this he will show you. I will do the plots and I will show it to you. So that you can try. You can ask me further questions. Then link axis plot 1, plot 2, and X means when I zoom in. When I try to zoom in, if I zoom in over here means here also it will automatically get zoomed. So that is this link axis. This function. Yes. Okay. Hello.
Sir, here like 2, 1, 1, what does it mean, sir?
Means there are two plots. Total there are going to be two subplots. One is my column 1, column number, and this is my row number. So this is column 1, row 1, which is this one.
Sir,
And column 1, row.
I guess in MATLAB, generally first rows and then columns will be given.
I don't know. Like, I think this is the way because it is getting plotted like this, right? If you want to understand, you'll have to go through the MATLAB documentation. There it would specify which is the column, which is the row.
Okay. Sir, please repeat once about the link axis.
About the
Link axis.
The link axis, I will show it to you. I will demonstrate. Okay. I will show.
So the GCF,
GCF is like, so it's sort of a handle for the current figure, etc.
Get the current figure.
Yes, so it is like it is setting, the color of the outside external color. GCA stands for the current axis, the axis, how we want the labels.
okay,
We want it to be bold.
okay, sir, okay.
These are just,
Okay.
aesthetics. We want it to look
Aesthetic.
nice. So for that it is not really important for understanding,
Okay,
but it'll look good.
okay, sir.
These are So you'll have to write these sets of code so that you can see your results, or you could either use a scope in Simulink and see your results. Okay. So this is my buck converter voltage mode control, and I will talk how this block diagram is written, is shown. It's like this over here. Okay, it will be like of this format. And okay, so this is my buck converter model. This is a custom model, okay, which relies on the mathematical equations of the buck converter, and it will have various subsystems. One is the switch node voltage, one is the inductor dynamics, one is the capacitor dynamics, one is the DCM logic block, all that. So all these things have been taught in the previous course, the NPTEL control and tuning methods, where they have demonstrated how you can generate these Simulink files, how you can make these custom Simulink files. These files have certain advantages, and we can, and hence they are used. So I'll actually just open the file actually. 1 minute. You guys are able to see my screen, right?
Yes, sir.
So you guys have MATLAB and all?
Yes, sir, we have,
Okay.
but we don't have this ready files.
You'll have to make them actually.
Yes, sir. Currently, I'm making them.
Once you make it, it is easy. Okay. So this was the initial file, okay, where I'm running buck converter simulation. So where I've shown what are these codes, etc. So I will open it. I will go for buck converter voltage mode control. If I want buck converter voltage mode control, I will select the file name as OP1. Okay. So now I run it. Should work. So it will take some time to execute.
Sir, there is a folder like lecture 21. Does it refers to the lecture 21 of this course or the previous course?
No, lecture 21 of this course.
Okay.
Yes. Okay, so it will simulate in the background. So till then I will explain here further. So this is how the Simulink file will look like. And there are something known as my pointer. So this is where I will store the data. So the inductor current, output voltage, my ramp voltage, all that data is coming to this bucks, and that is going to this buck underscore result. It is going to the workspace. So there's a thing known as to workspace block in Simulink, and I will use that to store the data. This is my custom made buck converter model, which consists of these 4 subsystems. And these 4 subsystems have the algebraic or the dynamical equations, which are written and which depend on the gate signals and the parameters of the buck converter, etc. And how this model has been made was taught in the previous course. So you can refer to that on how they have made the model. Next, the advantage of this method is, see these V in step, like this is my input voltage. Input voltage is just a signal. It is, if you use the SimScape value, you have to connect a DC voltage source. Okay, then how will you change the DC voltage source value, etc.? That is difficult. See, now if you make a buck converter in SimScape using Simlink, use SimScape in Simlink, you'll have to connect a physically an inductor, you'll have to connect a capacitor, you'll have to connect them. Then what the problem is when you want to measure the current flow into the inductor, you have to use a current measurement block. For voltage, you have to use a voltage measurement block. So for each signal, you'll have to connect that extra measurement block, etc. And that will, that is very tedious. It will not look good, etc. But using this method, the voltage value is just a signal. The inductor current is just a signal. So I can directly take those signal and I can directly plot it. I can directly see the result, etc. I do not have to use any extra measurement block and other stuff. So that is one advantage. Another thing is I want to change the input voltage, I want to change the inductor current, or I want to change the resistance. There are options which you can use in using those SimScape blocks, but they are limited. Like you can only change it by once or twice, etc. All that, or it might be a bit complex to do it. But over here we have this functionality where we just have to change the signal applied to this buck converter. Okay. So I hope it has finished running. Right. So this is my file. Okay. This is my buck converter. I'll open it. This has the various subsystems. Okay, various subsystems. One is for the switch node voltage. One is for my inductor dynamics. One is for my capacitor dynamic, and one is for my DC and logic block. So the logic behind this and the reasoning behind this has been explained in the previous NPTEL course, and I would highly recommend you to go through it, to understand it, to make the block and to run it and check. Once you make these blocks and run it, then you can reuse this file or your various other files, etc. Then this is my input voltage. Okay, my input voltage is just a value Vin. So what this Vin, the variable value Vin, is what I have defined over here. This Vin equal to 12. So when I write Vin over here, when I say my value is Vin, it will know. It will automatically write the value as 12. It will automatically consider the value as 12. Similarly, for DCM enabled, it will consider value 0, etc. And this is 1 by R, this is gain. Okay. So I'd like to know how familiar are you guys with MATLAB? Like how many of you?
Yeah,
Yes, yes.
we could understand, sir. Only this, what to say, the syntax and all we understand. These blocks we have seen before. We're just looking for the implementation, how it is implemented.
Okay, okay. What about Vinerji and Ajay? Do you have any other doubts?
Yes, sir, I have. I am familiar with this MATLAB and all.
Okay, okay, okay. So yes, so these blocks you'll have to make it. You can refer to the previous course. So this is my voltage mode control. My voltage mode control logic. This is my logic for voltage mode control. So my reference voltage is coming here. I'm subtracting with the output voltage from it, and that will generate my error signal. So this will be my error signal. That is going to my transfer function. Okay. I told the numerator coefficients, the denominator coefficients, etc. So this transfer function is like the controller. The controller will generate a signal known as vcon. This vcon will be compared with this ramp. Okay, it will be compared with this ramp, and based on that, it will generate the reset signal, and the set signal is given at a particular fixed rate. Okay, the set signal. So let me just open. Fine. Okay, so you guys are able to understand, you have doubts in this. This is the voltage mode control logic which is being run.
What, sir, what is the concept of audio susceptibility? Does it means like restricting the changes in the input to reflected the output or anything else?
No, audio susceptibility stands for the effect on the output due to input. Okay, so the audio susceptibility is high, that means it is very susceptible to changes in the input. But if the audio susceptibility is low, that means it is more tolerant to changes in the input. That means output is not affected as
Okay.
much by changes in the input.
Okay, sir.
Then, see, this is my
Sir,
model.
here Vn,
Okay, this Vn is
sir,
not.
Vn is no, it has a gain of Vn is multiplied with a gain of 1 by 12.
Yes.
So here it will become 1
Yeah, one
because
volt.
Vn
Yes.
is 12.
Yes.
Uh,
See, this is for actually, this file is for feed forward. It is not actual. You can ignore this one. I'll remove that. It is confusing actually. Or one, let me know. Zero. So we are ignoring the effect of veil. So this if this was there, it would result in some feed forward operation, but we'll not consider that for now. Okay.
Okay.
So just consider then multiplication also not happening. Just okay. So we'll ignore Vn. Vn, if we want to do feed forward operation of input voltage, then we use that. So actually in voltage mode control, it is line regulation is poor. That means it is affected by changes in input voltage. But its load regulation is very good. So if you want to, take into account the changes in input voltage, then we do input voltage feed forward. So that's why this Vn is there, but you ignore it for right now. So this is my ramp, and this is compared with this Vcon, and that will generate my reset signal.
yeah, okay, sir.
Any other questions in this? So my ramp value V underscore M, this is that value 10. Okay, this is that value 10. And 0 and T means the time period. Okay, from when it is happening, when it is repeating. See, this is my Vref, which is the value stored, that is 1, and Vref underscore step. And this T underscore step is a step time. So let me draw actually. So Vref underscore step is like this. This is a step. This is the initial value of it, and this is the final value of it. And the time instant when which the step happens is known as T underscore step. Okay. So effectively at this point, it will be value Vref. Then at time T underscore step, the value will be changed to Vref plus Vref underscore step. Okay. So this is how I can make changes in the reference voltage. I can similarly make changes in the current, load current. I can similarly make changes in the input voltage using this method. All right. Then the file. This is the inside the subsystem. This is the logic. We ignore Vn. Vn is for the feed forward operation. Okay. So what effectively is this logic is? This is my ramp. This is my beacon. And when it tries to go above, it will generate, this is my duty ratio. This is my duty ratio. So this is where the set pulse happens, and this is where the reset pulse comes. Set pulse, and this is the reset pulse. And these all are separated by a fixed time duration t. So when my VRAM becomes greater than VCon, when this VRAM gets greater than VCon, then the reset pulse comes, R comes, and then the Q becomes low. And when the set pulse comes, it goes high, and it is high like this. Okay, so this is the operation of voltage mode control.
Sir, this is trailing edge modulation, right?
Yeah, trailing edge modulation.
Because this reset signal is coming from the loop.
Yes, yeah. So now there are other various control techniques. There's the peak current mode control also, which we have seen before. That is when the inductor current tries to reach the reference value, then it gives that reset signal and it turns off. So this is the peak current mode control waveforms, and it is implemented in Simulink like this. Okay, we have a reference value and output voltage. We compare that, and we get a V error. Okay, this V error passes through my
Sir,
cut. Yes.
sir, this has a audio susceptibility problem, right?
Which one?
This mode of peak current mode control, if it is implemented as it is as shown by you. Like as there is no feed forward, only line load current will be regulated and the output voltage has the changes of the input voltage.
No, this actually is current mode control. So current mode control has uh, good line regulation and poor load regulation. Poor load regulation means when the load current changes, it takes more time to respond to that, but it has good line regulation, good input voltage. It can regulate it, because what happens is the input voltage information gets reflected via the inductor current. So that's why it has good line regulation. So its audio susceptibility will be poor. Means it will be less susceptible to changes in input voltage. This is for current mode control.
For understanding it better, I have to implement this, right?
Yeah. You
Or
have
is
to
there any
implement.
explanation for that?
See, the explanation is a bit complicated. Like what happens is the information of the changes in input voltage is reflected in the inductor current's slope. Okay, because the inductor current slope is M1, rising
V
slope,
in minus
Vn minus
V
V.
input minus V output by L.
So yes, so that information, if V input changes, that information is reflected in the slope of the inductor current. Okay, so that is that that is already inherently present in current mode control. I am using that slope information already. That is why current mode control
Okay.
is good line regulation.
Okay, sir. Okay, thank you.
Yes. So now I have the V error signal that generates my reference signal. So it passes through the controller and it will generate my reference signal. For the time being, ignore this ramp. This is my reference signal, this is my inductor current. So when my inductor current tries to exceed my reference signal, then it gives a reset pulse. Okay. And if it gives a reset pulse, that means Q turns off. And this set pulse comes periodically at a time. So, any doubts in this?
No, sir.
So this is the block inside that peak CMC, right?
Yeah. This is the block inside Peak CMC.
So everything else remains same. Only we are changing inside that.
Yeah. That's the advantage. So I have these all same. Only if I want to change what control technique, I can just change. So this is one advantage of it. So I recommend you to make all these files. Okay, first make the buck converter model. Then all these are given to you, right? So you can make the changes accordingly. Then similarly, we can have constant on-time valley current control also we can implement. We just change So the meeting will end in 10 minutes. So after the meeting ends, I'll again resume it. So now I will just change this block. I will use a constant on-time control block. And inside that block, what I have the reference voltage, I compare it with the output voltage, I generate my error. Will generate my error. That passes through this and it generates my reference current. This is my value reference current. So if you remember constant on-time value control, this is my reference current. My inductor current touches it, then it will be on for a constant duration. And it will again turn off. And then once it touches it back, then again it will turn on. So this duration, this is my T on. This is fixed. And this duration, T off, this is variable. And this depends on my loop. Okay, this depends on the loop will control my reference current, IREF, value reference current, and that will effectively control my off time. But my on time is fixed. So how I implement it, I generate the reference, I generate it, and then the inductor current is compared. So when the inductor current tries to become less than the reference current, then this will go high. This will become 1. So the edge detector is there. The edge detector will detect that the value has gone from 0. Earlier the value is 0, then it has gone to 1. So it will detect this rising edge, it will detect. Okay. And also there's a minimum off time logic also is present. So once it detects that edge, then it will be on for a duration of T on. Okay. It will be on for a fixed duration of T on. And after this, and this is a monostable multi-vibrator. And after it is on for this fixed duration T on, it will turn off. And that's why this gives the gate pulse. So this is my effective gate pulse, T on, and then it will be off. And once again, when that trigger comes, it will be on for the fixed duration T on. So this is my constant on-time control. This is a bit complicated to understand. And if you want to understand it in more detail, it has been explained in the previous course, the NPTEL control and tuning methods course, where they have explained in detail what is constant on-time value, current mode control, why we require a minimum off time. All of this has been explained in detail in the previous course. So I highly recommend you to understand it, go through the previous course video to understand how it is works, and then you'll be able to implement it smoothly.
So the output of edge detector will be 1, right? When it sees the transition at the input.
Yes, it will be 1, and that will, yes, that will be 1. And that will not be on, that will not be 1 throughout. Okay, it will be like this. It will just be a small edge, small value.
Okay.
Okay, and that small value will trigger this monostable multivibrator.
Okay.
See, this concept of okay,
yeah, tell sir.
So this concept of edge detection. See, at an edge, then we want to do something. Okay, so that so it will be very useful if you understand this over here in the MATLAB, because then afterwards in FPGA also we'll be using this concept of edge triggered event. Okay, based on an edge, either a rising edge or a falling edge, then I tell it to do some operation, or I tell it to delay it, or I tell it to be on for some fixed duration. All of that is controlled by an edge. Okay, so that edge detection is important. So there are FPGA codes, all this Verilog HDL codes are there for detecting edge, all that. But this is how we are implementing in Simulink. So once you understand this implementation in Simulink, then you'll be able to translate it into Verilog HDL code. Now, all of you do not have access to FPGA, all of you do not know Verilog HDL, etc. But you can learn this Simulink thing and you can implement this control logic. Then you will have confidence that you can that you have understood something. Okay. So that's why I highly recommend you, although it will take lots of time to go through the previous NPTEL course. Like if you want to understand constant on time, go to the constant on time control, what it has been taught in the previous course, understand it, make the file, simulate the file, and then you will have confidence, you will be able to understand the operation. Now see, you can tap each signal. You can see this signal, you can see this signal, all of the signals you can see on a scope. Okay, there's a scope option. So you can see each and every signal which you want. You can see the inductor current, you can see the reference current, all of that you can see on the scope, and you can be able to understand it and see it visually happening properly. And see, you will make it and it will not work. Okay, you will make it and it will not work. Then what you have to do, you have to see through the scope. You have to see what is not coming, what is the error exactly. So that is how you must debug and you must make it in Simulink. So it will take time, but it is worth the effort. So I'll proceed, or there's no other doubt. So
That is minimum off time block.
yes.
This minimum off time block is taking the input of a monostable multivibrator, and then the comparator.
Yes. Okay.
The output, what is happening here, sir?
So
Minimum off time.
what happens is there should be some minimum off time. Okay. So
Okay.
there should be this minimum off time.
Yeah.
So in this minimum off time, the edges which are detected, these edges which come, these edges should not turn. If another edge comes over here, then we'll turn on over here again and it'll be on for this constant on time. So that we want to avoid. So for that we use this minimum off time logic. Okay. So for the details of minimum off time is included in the previous course.
Okay.
So you can go through it.
Yes.
So now this is all for analog control. Now we want to make it digital. So for digital we need an ADC and we need a compensator. So for that we will start with an ADC. So we want ADC, what it does, it takes a analog signal and it converts into a digital value. So it takes a sample, it goes to the quantizer, there's a delay of the ADC, etc. All of this is there. So how are we
Sir, why there is a delay, sir?
Because the ADC takes time to convert the analog value into a digital value.
You are audible, you are not audible.
Is it clear now? Can you hear me?
Yes, sir.
Because the ADC takes time to convert the analog signal into a digital signal. That is why there's a delay.
That computation time and
Yes, the computation time it takes. The computation time is for the controller's operation. The conversion time.
conversion.
The ADC. Yeah.
In general, it is modeled as an RC, right? ADC. Charging of the capacitor. And
those are internal in the ADC. Those ADC stuff. Okay, there will be those internal capacitors, everything for taking the sample, holding that value. And for this, those are certain complex stuff. Here we are not modeling that using capacitors and using resistors. We are modeling that using triggered events. Okay, triggered events. So I'll explain that. So what we have is over here. This is a ADC block. Okay, there is the inbuilt ADC block also, but we have made our own custom ADC block. It is this constant one. Okay, so this is
it gonna end.
Okay. So I will, after the meeting ends, I'll again start. Okay. So this ADC is a subsystem. Okay, it has an enable block and it has a trigger block. This one over here. There's an enable option, there's a trigger option. And this means zero order hold. So what happens is, if I give value 1, means this ADC is enabled. Okay, this enabled. We want it to be enabled. So just give a constant value 1. Now this is a signal. It comes like this, comes like this, comes like this. So when the signal comes, I want the ADC to take the sample. So there's a zero order hold. What does the zero order hold do? If the input was some value, it will hold that value. Like, I mean, the signal is varying like this. It will hold the value here. It will keep it fixed. Then when the next trigger comes, it will take the sample, it will keep it fixed. Next trigger comes, it will take the sample, it will keep it fixed. Next trigger comes, it will take the sample and keep it fixed. Next trigger comes, it takes the sample here and keeps it fixed. So this is how the zero order hold block works. Okay, and the trigger is externally given via this block. Or we can have another, or we can have an event triggered event, or it could be a uniform sampling event. Any doubts in this?
Sir, the at the every rise time of the on pulse, at that time trigger will come, right?
Yeah. When it is high, that is the trigger.
Okay. That is the time it will take the
Sample. Yes.
sample.
Yes. Yeah. Mhm. So this is for my ADC. Next, we will consider the compensator. So we spoke how that Kp, Ki, Kd. Okay, those are my proportional integral derivative gains. In analog domain, they're there. Now we want to implement it in digital domain. So how do we implement in digital domain? We'll consider. So this is my block diagram for PID controller in digital domain. Okay, we know that Z inverse, Z inverse. Well, we have Z transform. You guys would have learned in engineering. So this is used for digital control systems. For analog control systems, we use S, but for digital control system, we use this Z. Okay. So this is for my proportional gain, this is for my integral gain, and this is for my derivative gain. So if you see this is my V error. Okay, we'll see it further. So this is the transfer function, overall transfer function of this block. This overall transfer function is given by GC of Z. And then we can factorize, we can get it of this format. Which I actually forgot to tell this linked access. Banerjee was talking about, asking about. So if I zoom, if I'm zooming this, see, if I'm zooming this portion, I'm zooming in the top subplot. But that same zoom must happen even in the down subplot. For that, I use that link access command. All right.
Okay. Like what is the syntax, sir? Link access
What is the
syntax.
link access? That is, I forgot. Link access plot 1, plot 2. PLT1 is a subplot, and this is PLT2 is the next subplot.
Okay, for X and Y, you have to include Y too, right?
Yes, I'm just including X, means I'm just doing it in time axis. So now if you see, if I
Okay, sir.
zoom it over here, it will not zoom in this
It
plot
won't
because
reflect.
they are not
Yes,
linked.
sir.
Yes.
Yes, sir. Thank you.
Yes. So this is for this. So now I'm a different file. So let this run in the background. So what I was telling, Acha,
KP.
yes. So this is, so we can implement this PID controller using a built-in PID controller block in MATLAB. But there are limitations for that block, and so we had to use these difference equations. So I will first explain these difference equations, then I will talk about the limitation. So the output of a KP block, GC of Z, VC of N VE of n is the input. It is multiplied by gain Kp. And then you get Vc of n is equal to Kp into VE of n. Okay. Kp into VE of n. Now, let us consider proportional integral control. If I have a proportional integral control, what actually happens? So these are my difference equations. Okay. So my Vc of n, that is my controller output, is equal to Kp into VE of n plus my Ui of n. Okay, Ui integral of n. And my U integral of n is equal to Ki into VU of n plus Ui of n minus 1, which is a delay. See, that Z inverse causes a unit delay. Okay. Instead of that, I'm using a register. I'm using a register to store the previous value, and that register gets updated at a particular event. So why is this important? Now, if I had the normal, I had a normal digital PI controller. Okay, the normal digital PI controller. It will operate, say, at 0, at t, at 2t. What it will do, it will take the sample and it will generate a new VC of it. Sample, take the new one. Sample and take the new one. But what if I don't want it to happen at 0t and 2t? What if I want it to happen over here, and then over here? Then I want it to be controlled by me. So if I want it to be controlled by me, I want it to be controlled by some particular event which I have decided, not a predefined one. So if I want it to be controlled by me, what will happen at this event? It should come some value. And when this comes, it will update its value. Then when this comes, it will further update its value like that. So I want it to be customizable by me at the instant I want it to update. It should be controlled by me. So for that, I use this event thing. And when I use this event logic, these are the difference equations which it will implement to update the value of my controller. Okay, so this is based on a particular clock which is driven by me. Any doubts in this?
So
Yes.
what you have said here, right? So like I delay custom block. Could you please repeat it once?
Okay. See, if it was a normal digital PID controller in MATLAB, in Simulink, it will take at 0, it will take a sample and will update the value. Take at t, it will take a sample and update the value. It will have a particular switching frequency or sampling frequency that is fixed. Okay. But I don't want it to happen. I want it to happen at one particular event which I define. I say now you update the value, it should update the value. Next I give another command, update the value, it should update the value. Next I give another command, update the value, it will update the value. So these commands, it doesn't need to be spaced at a time period t. It could happen after time period of around 1.2 t also it can happen. That is fine with me. But I want it to update the value based on only when I give the signal that you have to update the value. So I want to design a PI controller like that.
Simulink, like MATLAB Simulink at a particular time intervals only we can take. But if I want for first time at t and for second time at 1.2 t, then we can't do that with the Simulink block, right?
Yeah, yes, that is a limitation of that. So we have made our custom block.
Okay, sir. Thank you.
Yes. So similarly, for the PID controller also, we can implement that. These are the difference equations. And this is how it is implemented in MATLAB. So what I have is, these are like errors, not error. It's like it is delayed. It is giving a delayed value. Like the storing, it is working as a register. So this is my beacon. Let me use pen. So this is my beacon. That is, it is the from the KP from KI and from KD. Okay, this is my proportional, this is my integral, and this is my derivative thing. So KP into V error comes directly here. KI into V error plus the previous value of UI, that comes out over here. Then KD and V error minus previous error into KD, that is my derivative part which comes over here. So now I want this previous values. I want to store these previous values. So what I do, I take the current value of UI. Okay, I take the current value of UI. I pass it through a delay event, through a register, okay, which delays it. And this comes out as a previous value. UI previous is the delayed version of UI. It is delayed by one signal. It is delayed by one signal. Any doubts in this?
Sir,
Yes.
here in this UI previous.
Yes. One.
Okay.
Okay. Here.
Sir, in this UI previous, until the next trigger signal comes, this memory will hold the previous value.
Yeah.
Okay, that okay. Until the next trigger signal, that value will be given as input to this VE previous.
UI previous or VE previous, yes.
Sir, why we need this enable always, sir?
Okay, this enable is not required actually, but they have just given that functionality.
Okay.
I didn't understand like why UI previous and VE previous. Could you please elaborate it?
No, in the difference equation, in this difference equation, I need UI is KI into V error plus the UI previous value. So for that, I need to know the previous value. That is why I'm storing the previous value.
VE of error is okay, but why we required a UA of n minus 1, sir?
See, basically it is integral control. If it was continuous time integral control, what happens is, this is my V error. Suppose my V error is very like this. What is my UI will be the integral sum of this. What is the sum of it? That will be my UI. Okay, that my UI will be the UI, which is basically be the integration of all these errors. That is the area under this curve. But now I'm going for discrete time. So what I do, instead of integral, I am doing a summation of the errors. Okay, I'm doing a summation of the errors. So assume it was summation I going from 1 to n, b error of I. Okay. So now one more error comes, plus VE of n plus 1 comes. So what I want to do is, my UI of n plus 1 is actually equal to VE of n plus 1 plus summation I going from 1 to n VE of I. But what? So if I use this summation, I need to know all the old previous errors, but I don't want to know that. What I know is UI of n is the summation of I going from 1 to n VE of I. That is why my UI of n plus 1 is equal to VE of n plus 1 plus UI of n. Okay. That is why I need this term.
Yeah, from starting where you have started, like UI equal to integral VE of dt, that is fine. Later on, this dt equal to summation VE of n. What is this dt, sir? In digital domain, you are saying?
Yeah, I'm talking of digital domain.
Discrete time.
Discrete time or digital domain. Fine.
Okay, discrete time is equal to summation of like V of n, that's fine. Later on, this I equal to n to, you are saying n plus 1. I of n plus n plus 1, why you have written, sir?
See, UI of n plus 1. UI of n plus 1. At the n plus 1th instant, that UI will be the sum of all the previous errors. previous errors till n and v of n plus 1. All those errors it will add up, right? That is why I written like that.
I didn't get it, like for a DT, you are for I equal to 1 to n, but then I equal to 1 to n minus 1, we have to write it like uh, I equal to 1 to n minus 1 v of I plus v of n for the DT in the third step.
Okay, actually dt is the wrong thing. 1 minute. Okay, let me write it somewhere slide. 1 minute. Okay, right over here. Okay. So my integral, this is equal to summation I goes from 1 to n. My error. Okay, the error at each of the sample instant, I add it. Okay. My ui of n plus 1 is equal to summation going from I equal to 1 to n plus 1 ve of n. So this I can write it down as ve of n plus 1 plus summation I going from 1 to n ui of n. Oh, sorry, ve of n. Ve of n. So effectively, ui of n plus 1 is equal to ve of n plus 1 plus ui of n. Okay.
Okay. Okay, sir. It's
Sir?
pretty clear now.
Yes, yes, yes.
Sir,
Yeah.
here knowing the error up to the previous sample is equal to ui of n.
Yeah, yes. The summation of the
Summation
previous
of
error.
summation of all the previous error
Hmm.
up to n is equal to ui.
Yes, is equal to ui. Yes, yes. Yeah. Yes.
Sir,
Okay.
but here we are not taking all the errors, like just we are using the previous error only, right?
We're not using the previous error. We're using the summation of the previous errors. The summation of the previous errors we are storing.
But in real time, it will keep on going increasing, right?
Yes, yes. That is the advantage. That is why, suppose, let me see. Let us say 1 minute. We have v error of 0. Then v error of 1 comes. Okay. So I have ui of 0. I have ui of 1. So ui of 1 is what? It is v error of 0 plus v error of 1. ui of 2 will be what? V error of 2 plus V error of 1 plus V error of 0. I don't need to remember V error of 1 and V error of 0. I need to remember the sum. So it will be V error of 2 plus Ui of 1. So all I need to know is I need to store Ui of 1. Okay, now let us consider Ui of 3. Ui of 3 is what? V error of 3 plus V error of 2 plus V error of 1 plus V error of 0. This is the present value which I get at the input, and I just need to store the summation of all this. So this will be equal to V error of 3 plus Ui of 2. Okay. So I don't need to store the errors. I just need to store the summation of the previous errors.
Sir, but in this case also, like if the like I'm storing the UI has only 3 bits. Like after if the error exceeds greater than 8, then I can't able to store, right?
See, bit, this is not bit. Okay. V error of 0 might be like 8 bits. V error of 1 also is 8 bits. V error of 2 also is 8 bits. When I see, these are the same, their bits are the same. I just add their values. Okay.
Okay.
Sir,
Yes.
Okay.
sir, where in the diagram this VE changes to UI? Can you please show some? All the VE previous is changing to UI.
Yes, yes. See, actually, I have not included the gain. There is a gain KI that I have not included. I have not included
Okay.
that. When I included that, there will be a change. But since I have given KI to be equal to 1, then UI will be equal to VA. Okay, otherwise it should be with that gain.
No, sir, not KI. This UI, because all this VE, previous VE, error
Hmm.
VE, we are writing it as UI of n or UI of 2.
Yes.
Where it is changing from, all previous errors are changing to UI in the diagram, in the
No,
block diagram, or
no, what actually I'm doing is UI of 1 is V error of 0 plus V error of 1. Okay, I store that sum. Okay, you're talking the block diagram. This diagram here, over
yeah,
here.
yes, sir. Somewhere, yeah.
Yes. So this is KI. Okay, this is V error of n. Okay, here I get KI into V error of n. Okay,
Oh,
and this is my UI of n minus 1. That I add and I get UI of n. That's why this is this
okay.
difference equation. UI
So
of n.
in this register, all the previous summation of all the previous errors were here.
Yeah, exactly.
Okay, sir.
So I'll proceed further. Now we'll consider digital voltage mode control. Okay. Actually, Manjunath, the recordings are uploaded on YouTube. So I'll send the YouTube link. 1 minute. So I'll send the YouTube links, link to the YouTube channel as well as link to the slides for you. So this will be uploaded also further. So you can access it there. Okay.
Okay, sir.
So this is for my digital voltage mode control. This is my implementation Simlink file. Okay. These all extra things remain the same. Basic change is the digital voltage mode control block. Okay. This consists of what? My V reference. Okay, this is my V reference. Then I have an ADC. Okay, it is an event triggered ADC. When it is giving the command that you must take the sample, and that command is generated by this, then it will take the sample of my output voltage. It takes the sample of the output voltage, and that sampled output voltage is subtracted by the from the reference. So when I see how frequently do these videos get uploaded over there?
Sir, they are
Available. So that is accessible for everyone, only for those who are enrolled in the course.
I guess
enrolled.
for those who enrolled on the course.
Okay, fine. Okay. So my V reference minus the V output N, that generates my VE of N. That goes to my digital controller. And my digital controller has this logic which I have shown you. KP, KI, KB. Okay, there's a KPD means for proportional gain in digital domain. KID is for integral gain in digital domain. KD is derivative gain in digital domain. So to convert from this is my analog KP, KI, KD. Okay. Just one. KP, KI, KD. Now when I convert it into digital, KP remains the same. KI gets multiplied by the sampling time period and KD gets divided by the sampling time period. Okay. That is how we convert PID gains from analog domain to digital domain.
These conversions we'll see later, is it, sir?
No, this is the standard
How?
convention.
Oh, this is standard. Okay.
Yeah. See, there are other. See, these standards are, I think, based on Euler's backward method, all this stuff. There might be different methods as well, but this is one of the approaches which is there. Okay.
Oh,
Yeah.
okay.
So this is the way, and this is the PID controller which we have implemented, and that generates my vcon. Okay, that vcon is again compared with my RAM. So this is the logic is the same. Only changes I'm using an ADC. It is generating a digital value which is compared with my V reference, and then for V error it is passing to a digital controller, and that is generating a digital vcon. Okay, that is compared with my RAM, and that is then the set reset SR latch logic is the same. Okay. So these are the simulation results. This is my inductor current. How the inductor current is changing at this t at time t 2 millisecond. That is where I have given a step change of the reference output. I have told the step output voltage to be decreased. I think. Let me just see what is the command. Achha. No. At this step 2 millisecond, the input voltage is reduced from 12 to 8. 12 minus 4, that is 8. Okay. So when that change happens, this is how the inductor current varies, and this is how the output voltage also varies. So what's happening is the output voltage is affected by the change in input voltage. No doubt it is getting affected, but it is again regulating back to the reference value. Okay. So this is how the inductor current also undergoes a particular change. And this is how the output voltage graphs look like. And if you further
So why
see,
there are two waveforms here, sir?
yes, that will explain further. So you see, this is my actual analog output voltage, and red is my digital output voltage, the sampled output voltage. Okay.
This is
These are the sampled output voltages.
yeah. This is sample during off time. Trying to sample.
It is sampled during off time. Okay.
Sir, why in this subplot both are showing differently, sir? Two windows are coming.
Yeah, it has been the file user has given that logic. We can modify it and plot it on the same plot, but here they've modified it. They've plotted different figures.
Okay, so there we gave 2, 1, 2 like that. Here
Yes,
they made a differently.
yes,
Okay.
here actually they have different. Different figures, figure 1 and figure 2. They are different. Okay.
Okay, sir.
So this is how it. So if we observe this, even though there is a change in input voltage, finally the inductor current also retains its same value because the load current has not been changed. Similarly, the output voltage finally gets regulated back to its original value. Okay, although it takes some time. So this is the implementation of digital voltage control. So if there are any doubts, any questions in this? So if there are no
No, sir.
doubts, okay. So see, I can just show you these demonstration, but it will not make any, won't be of much use to you unless you go make the file and simulate it and check it, cross check, verify, play around with the values. All right. So that is important. So that is the effort which you have to do. That I cannot do it for you. Okay. So this course you have lots of things to learn, but this is something which can be learned in a more easier manner. Okay. And you can have some certain results and you can know, you can show that you have done something. Right? So then
Yes, sir. It will help us to do it faster, sir. Or
yes.
yes, your understanding. Okay, sir.
So this for digital voltage mode control. So we will proceed with let's see. Peak current control. So we'll consider mixed signal control. Okay. So how is it in mixed signal control? We're taking the output voltage sample, V output, and we are getting using an ADC. Then with V reference, we're comparing it, we're getting a V error that is passing through a digital controller, which I told it must be that event based. Okay. Then that is passing to digital analog converter, which is generating reference current. In MATLAB, we are not using digital to analog converter because it is just a value, it is just a signal. But when we are practically implementing, we need a DAC, digital to analog converter. Then we need a comparator. So the comparator operation is happening in Simulink using what you say greater than or less than block. Okay, greater than or less than block is used for comparator operation. SR flip flop is there's a SR latch is there. Okay, dead time actually we are not including it in our Simulink file, but when we are running it in hardware, we have to implement dead time as well. So these are the plots. So this is how my inductor current is varying. When it tries to reach the reference value, then the reset happens and its switch turns off. So I am taking the sample prior.
Sir, here, like the I reference it comes based on the output voltage, right?
It comes based on the outer voltage loop. Yes.
Okay.
Mhm.
Okay. And it is interval 2 sampling with TS delay.
Yes. Yes. Yeah.
Okay, sir. Okay.
Yeah. So FSW is my set pulse. This is my set pulse, which is coming after fixed time period of TS. But my sampling pulse is shifted prior to my set pulse. So just before the inductor is turned on, the switch is turned on, the main switch is turned on, I'm taking the sample, that is V output of it. And okay, and I'm using that sampled value for my computation, for my controller to work with. Okay, so this is my peak current mode control logic. Hmm. So file is simulating. So any questions till now or any doubts? So what about the previous lectures, previous weeks also? Is there any doubt or anything? Any question you're facing?
I have issue with understanding interval 2 sampling with 1 cycle delay.
What exactly is the doubt?
So that actually they are taking the sample at the crossover point between the on and off.
Hmm.
In, in all the lectures, it is shown like that. Like
Okay.
FSW and FSM are exactly at
Okay.
the
At the same
sharp
point.
corner.
Okay.
Yes, but they are saying it is with interval 2 sampling with 1 cycle delay. They are saying I'm confusing like at that particular point of a sharp curve valley point. How
Mhm.
can they judge whether it is during the off time it is taken or during the on
Yeah.
time it was taken?
So in the practical implementation, what happens is you take the sample and then you turn on the switch. Okay. So there is a delay which is there because of the gate driver. They'll get a propagation delay and all that. So you take the sample, there'll be a small delay, and then the switch will turn on. So you're not exactly taking the sample at the value.
Yes, but in the lectures it is given like that at the sharp corner it is taking and they are saying interval 2 sample.
Yes, yes. But in the practical implementation, it will not be like that. Okay.
It's like, but we can't say like at that point we are taking and it is interval 2 sampling. If you are saying it interval 2 sampling, the sampling must be taken before the start corner, right?
Yes, yes, yes.
Sir, here in the output voltage V0,
Mhm.
this blue form is the reference, right, sir?
No. Blue is that how it is varying in analog domain.
Okay.
It's the actual voltage of the output voltage. But then we are just taking individual samples at one sample per cycle. That the
Okay.
sample values are the red and the actual output voltage is the blue. Okay.
Okay.
So simulations on now. So this is my mixed signal peak control implementation scheme. The output voltage again is sampled using ADC. And that is compared with the V reference. It goes to my PI controller that generates my peak reference value, and that is compared with my inductor current. The comparative operation is happening using a greater than or less than block. And then that goes to my reset. My set is given by my fixed time period switching pulse. Okay. And these are the waveforms of the inductor current waveform as well as the output voltage waveform. So here they are given a reference. The output voltage is changed from 1 volt to 1.05. So change in the reference of 0.5 volt. So the blue one is the actual output voltage and red one is the sampled output voltage value. Okay. So we will see where the sample is being taken. This is where the sample is being taken. Okay, and that sample signal is coming after delay of t underscore s. Okay, it has the same time period of t. It has a delay of t underscore s. But a normal switching pulse has a delay of 0. So if you will see the plot, this is my FSW, and after a delay, I am taking the sample, and that delay is 0.9 into TS, or effectively, this TS over here is 0.1 into TS. See, from here to here, this is 0.9 into TS into T. Okay, and then this TS is 0.1 into T. Is that making sense?
Yes, sir. Totally after TS, we are giving that sampling.
Yes.
It's 0.9 T plus 0.1 T.
Yes. Okay, so these are the waveforms in the plots, and yeah, so you guys will have to make the plots and simulate it, make the files and simulate it. And this is the control logic which I've shown, and this extra things all of them remain the same. So that was for mixed signal control. Now we'll discuss about digital control.
Let's repeat once like 0.90.
What one? This
Yes,
this part.
0.90 on.
See, this
Okay.
is my switching pulse. Okay. I'm delaying by 0.9 t and then I'm giving the sampling pulse. That is how it is implemented in my Simulink.
Yes.
Sir?
Yes.
But 0.20, how it is getting?
Because the time period effectively is t, right? Effectively, the time period is capital T. That's why. So what I have, what let me take a minute to. This is
Sir?
happening. Yes, one minute. This is happening like this over here. This is my switching pulse. I'm giving a delay of 0.9 t, and then I'm giving this pulse. So this is the same pulse, but it is delayed by 0.9 t. So now the effective duration between this and this is 0.1 t. Okay. Ajay Sekhar, you were saying something?
Sir, actually this FSW is setting this queue.
Yeah, yes.
Sir, but for resetting, uh,
It is coming
for
from this
resetting
thing.
how, yeah, it is getting, but where that signal is, that R signal coming to R is what, sir?
Okay, that was shown in the ceiling file, no, actually. Need to take time. So here's what will happen over here is the reference, there's a greater than or equal to. There's a block less than or equal to. And there's
Yeah,
my I
okay, sir.
reference and this is my I. So this
Ah.
goes to my reset.
Okay.
Hmm.
So this, okay, when I reference IL become less than I reference, this reset will be
No,
happening.
when I reference becomes less than I. Now that means IL
Okay.
increases. IL becomes more than I reference, then the reset is. That is actually your
Okay.
peak conversion approach. When IL tries to become
Yeah.
more than I reference, that time this
Okay.
reset must be.
Then this reset is this voltage is controlling the reset. Set is controlled by FSW. Is that the way we have to?
Yes,
Okay.
yes. So this is the trailing edge modulation technique. Peak control. The set pulse is given. Set pulse is given at a fixed interval. Okay, a set pulse will come
Okay.
at a fixed interval.
Yeah.
When the reset pulse comes, depends on the loop, on my loop,
Okay.
outer voltage loop. Okay,
Okay.
that is how it works.
Okay. That's it.
So now we proceed to digital current mode control. So in digital current control, what happens? The output voltage is in digital domain, and the inductor current also is in digital domain. So this is the waveform. So what I have is I take the output voltage, I take the sample of output voltage, I even take the sample of inductor current. I take the sample of inductor current as well. So I'll take the sample of this. My blue trace is my actual inductor current. My red one is my reference inductor current, and my octar color or orange color, that is my actual emulated current. Okay. What happens is how the emulated current works is, let us consider for this cycle of emulated current. What it will do is it will take the valley point sample of the inductor current. This is my valley point, this is my inductor current in this cycle. I take the sample value of that, and I will use this sample value information in my next cycle. And to this sample value of inductor current, I will add my ramp. I will add a ramp. This is how this emulated current is generated. So there is a delay of one cycle delay of one cycle, TS. Okay.
So basically, where we are in the current cycle, we are using the sample in the previous cycle
Of the inductor
plus
current,
the
yes.
sample. Okay.
Okay. Plus the
Plus we are adding the current value, or what we are doing.
we are adding a ramp. We are adding a ramp.
Oh, ramp. Oh, ramp is starting from that value.
Yeah, ramp is starting from the previous valley point of the
Previous
inductor
one.
current. Yes. See, what happens is because we are doing sample, in the previous case, if you saw, this is my current. Okay, this is my current, which is compared. This is in the analog domain. If I just take a sample, it will be just some value over here, which is, let me place pen. If I just take a sample, it will just be a value over here like this. It will be constant. It will not be this changing graph. Then I will not know when to reset, right? So to give
Yeah.
that reset operation, I have to emulate that ramp. So I'll have to emulate the rising slope of the inductor current. So I will add some ramp, a ramp of one particular slope or some slope. So that is what happens
Okay.
in digital converter. I add this ramp. Yeah, I'll add that ramp, and when it reaches a reference value, the switch will turn off. So the one point to
What is
notice.
the difference between the previous one and this one, sir?
Okay, in the previous one, what is happening is there's this inductor current, the blue trace. Okay, this is my inductor current. The actual inductor current is compared with my reference. In the previous case, that is the mixed signal current mode control. In this fully digital current mode control, what I am taking is I'm using the emulated current is compared with my references. Ochre color one is compared with my reference. Okay, this emulated current signal is compared with my reference.
Sir, this method is not clear.
Yeah. Achha, so what in previous mixed signal control control, I'm taking the output voltage sample, and from that I am generating my reference. So that is the same. In fully digital also, I'm taking the output voltage sample. I'm taking the sample of the output voltage, comparing the reference, generating error, and that I'm generating the reference current. So all that is same. Okay. The only change is I'm using IE instead of directly using IL. That is the change. So what happens is IL is like this. Okay. If I just take the sample of IL, I'll just have a value like this, some value like this. This fixed value cannot be compared with some reference. Okay. This fixed value cannot be compared with some reference because I need the information. I need this sort of slope. I need this sort of rising slope. So to get that rising slope, I add a ripple emulator. I'll add some sort of ramp. I'll add a ramp signal. So that ramp signal should come. I will need to take the sample. I'll need to take the valley point. I need to take the valley point sample of the inductor current. So what I do, I take the valley point sample of the previous. I take the sample value of the previous inductor current sample, and then I store it for a time of TS. And then in the next cycle, I use that sample value of inductor current, and I add a ramp of slope MC. And when that emulated current reaches this reference current, then it will give the reset thing. And when it gives the reset, then my switch will turn off. Okay.
Okay. Sir, how who defines the slope of the ripple emulator?
Okay. So this slope of the ripple emulator, there are some research papers on how they decide the slope of the ripple emulator. Based on that, they do it.
Sir, that slope also seems to be changing after every cycle, right? Because the slope also after every switching cycle, this slope seems to be changing because this sampling point is increasing.
Okay, see, this slope MC is fixed. Okay, MC will be fixed. Okay, sample point will change, but MC will be fixed. Okay, the slope of MC will be fixed. It can be updated, all that is there, but currently just assume that it is a fixed slope.
Sir, if you take, my doubt is, sir,
Mhm.
if I take in that emulated inductor current,
Mhm.
if you take the last, that the green dotted line is ending at one point.
Yes, yes. Okay, okay. This point you're talking.
If yes, sir, in that point,
Uh,
if the inductor current starts to increase again,
okay. No, but then I'm turning off the switch now. When I turn off the switch, then the inductor current will start falling automatically. No?
okay, we're off.
Yes. This is the switch signal, the Q. So once I turn off the switch, then it will start falling automatically. Because what happens is the VL applied across the inductor becomes okay. Let us not go to that, but I turn off the switch, then the inductor current starts falling. So that's why I don't need to consider the ramp in this part when it is off. I only want to consider the ramp when it is on. So that is why I need the valley inductor current value.
Okay.
Sir, in the ripple emulator, like only we are getting only one cycle and the some half cycle, like for off time it is like
It is
uh,
disabled, sort of. It is not working, you can consider.
oh, for only on time you are increasing that slope, or and for off time you are disabling that ripple emulator, right?
Yeah, yes.
Okay.
Okay. So this is the sample value of inductor. I'm taking the sample. This is the valley point. Okay. This is my valley point. I'm taking that sample and I'm storing it. So the black trace is the current sample of the inductor current. And after I give a 1 cycle delay, it is a green trace. So green trace is this, you give a 1 cycle delay for the sample values of the inductor current. So this is how it is implemented in our Simlink logic. All right. And then on top of that, we add the emulated ramp. On top of the delayed 1 cycle delayed sample of the inductor current, we add the emulated ramp. Okay, so this is how it is done, and this operates using an integrator, a resettable integrator. See what is happening, it is rising at a slope MC, okay? It is rising at a slope of MC, it is a ramp. So when the switch is on, when Q is 1 and MC is a fixed value, what will happen is I'm giving the input to this function block, and then it will start rising at the slope MC because Q is 1. When Q becomes 0, what it would mean is I want to reset the ramp. That means I want to bring back the ramp to 0. Okay. So that is included in this logic. And that happens using an integrator. So what happens to the integrator is when Q is 1, okay, when Q is 1, I will get a value of MC over here, and integrator will generate a value of MC into T. Okay, integrator, see 1 is like a MC into 1 is a constant. So integrator will give MC into T. Then when Q becomes 0, it will reset the integrator. It will reset the integrator back to 0. So this is how it works. This is how we do that. We generate the ripple emulator and we have done it in the Simlink block based on this logic. Any doubts in this? It's a bit complex.
So
Yes,
the Q equal to 0 is the reset signal.
Yeah, reset. See, Q either takes value 1 or 0.
1.
When it is on, Q is 1. When it is off, Q is 0.
When Q is 1, it does the integration.
Yes, when Q is 0, it is disabled. Well, not disabled because we are giving input 0. And we have also reset the integrator to 0. Okay. That's right.
Please repeat this logic once.
Okay. So Q decides whether the integrator is, Q decides the input. Okay. If Q is 1, then the input to the integrator is MC. Okay. If Q is 0, then the input to the integrator is 0. If the input to the integrator is 0, then the previous value of the integrator, it will remain at that previous value. Now, the input to the integrator, Q is 1, let us assume. Now, Q is 1, the input to the integrator is MC. And what happens is the integrator will integrate it. So the output of the integrator will be MC into T. Okay. Now, when Q becomes 0, the input to the integrator will become 0. But we don't want it to be stored at this value. We don't want it to remain at this value. We want it to come back again to this value. That is why we give that reset option. So when Q becomes 0, we reset it to the previous value, or we reset it to 0.
Like
Whenever
it is falling edge triggering, right?
yeah, falling edge triggered, yes.
Okay.
That is why, because when Q is falling, Q is falling, that's why it gets triggered.
Sir, this MC and Q comes from the previous outside of this ripple emulator.
Yeah, they are the external values. Q is the signal, Q is the signal, and MC will be some constant value.
Q is the inductor current. What? Sorry.
No,
Q is
Q
what?
is my signal of the gate pulse, right?
Okay. Can you show the previous block, sir? This is actually a subsystem, right?
This one.
Yes, sir. To this reply, where is the MC and Q comes here?
So MC on this
To be.
internal line. It will be there,
Okay.
MC will be there.
Mhm.
And this is the Q which will come from externally.
Sir, if the emulated current slope is same in the current slide, then the on time will differ, right, sir?
Yeah, on time differs, yes.
Okay.
That's why
Because the starting point is different.
yes, that's why over here it is different. No, dn minus 1 ts is different from dn into ts. That is visible in the graph.
Okay. Yeah, okay, sir. We can proceed.
So variable current mode control also there is the same thing. The mid signal constant on time control is there. Again, ADC is there, samples output voltage compared to reference, generates the error. Then from the controller, we update the value that we use with the comparator, and that generates an event. We have the minimum off time logic and a bonus shot timer, which will generate the fixed on time. And with the dead time, it goes to these switches. Similarly, we can have a constant off time. In constant off time, it is opposite. See, this has become changed.
Why we need like these many number of events, sir? Like we are having here 3 events.
This is what wait, this is the same event. This, and this is the same event. So
Yes, sir, why those many events are required?
no, 1 minute. So this is the event. This is the generates the event that when the valley current becomes more than the inductor current, then it generates the event. Okay, it goes high for momentum. That is the event. When this event happens, I tell the ADC you must take the sample. I tell the controller you must update the value. That is why these events are there.
Okay. Okay, sir.
So constant on time, this is valley current mode control. So these are the polarities. For constant off time, it is peak current mode control. So that's why the polarities get interchanged, but the logic remains the same. And then for hysteresis current mode control, this is the logic. You take the sample and you take, okay, as you had pointed out last time, this RS flip-flop is in the digital domain. It is not in the analog domain. Okay, so all these files were simulated by Sir, and you can also make those files, make that logic, and you can simulate each of these modulation and control techniques.
Sir,
Yes,
sir, in the previous slide,
yes.
can you just that portion of this minimum on time and monoshot timer, this portion alone you please explain, sir, with
Okay.
this event trigger.
Okay. So when the event occurs, that I have to keep into consideration. So this is constant off time control. All right.
Yes.
So it will that event. Okay. whenever that event occurs, see there's an event which is occurring. It doesn't mean that whenever that event occurs, the monoshoot timer should get triggered and it should generate fixed off time. Let me do it for constant on time. It will be more easier to understand. So whenever the event occurs, T on will be on, and then it will be off for some time, and then again the event occurs and it will be on for a fixed duration. But I
Yes,
need to give some minimum off time. Okay, if this off time is very small, then what will happen? The switching frequency will be very high. There will not be enough time for the energy stored in the inductor to be transferred to the capacitor. So I need to have some minimum off time. So what happens is the event occurs, the on time is there. Then I have this minimum off time. Okay, minimum off time. So any event which comes over here, it will ignore. Okay, it will ignore those events. And then only after this
Okay.
minimum off time is elapsed and another trigger comes, then only it will turn on. Okay, so that is why this minimum off time logic is there.
No, that is the purpose of that monoshoot timer.
No, that is the purpose of this minimum off time. The monoshoot timer
Okay.
generates this fixed on time. Okay.
Hmm.
Hmm.
Okay, sir. So this it should ignore the
Ignore these
transition
triggers.
happening during the off time.
Yes, sir. Ignore the transitions, the events happening during the minimum off time. Okay,
Minimum off time.
this is the minimum T off which is required, which I want, which I've designed that it should ignore those things. After that minimum off time, then the event comes, it will then accept that and it will turn on the switch for the constant on time.
Wow.
Okay.
Oh. Okay.
Yes. So then we can end the session for today. And yeah. Any other queries or anything?
This variable frequency simulations are available in the lectures. I don't know.
Yeah. Variable frequency simulations also there. I've not shown it because we've actually done it got
Okay.
quite.
Okay. Okay.
That's why. Yeah.
We will do it, and if you have any doubt, we'll ask, sir.
Yes. You can ask. Okay.
Okay.